Hi, my name is Philip, and I will introduce our paper, Replay Overshooting, Learning Stochastic Latent Dynamics with the Extended Kalman Filter. This work is done in collaboration with Albert Lee, the co-first author of this paper, and Monroe Kennedy. Humans have world models that allow for accurate prediction. We are interested in allowing robots to learn similar models. And while simple physics-based prediction, like the trajectory of a ball, can be analytically determined, more complex tasks, such as contact or human motion, can be difficult to model. Furthermore, while there is an increase in the abundance of collected data, direct access to the state is not always possible. This brings us to replay overshooting, a method for learning a time series model capable of accurate long horizon prediction. In addition, replay overshooting does this in a way that utilizes properties of the extended Kalman filter. We show our models are parameter efficient, benefit from a strong training signal, learn meaningful latent manifolds, and balance accuracy with uncertainty. There is a large body of related work, which we split into three main categories. It's typical to learn a dynamics and observation model as we do in replay overshooting, but beyond that, inference models are diverse. A common approach is training a recurrent inference model that consumes observations and returns states. These methods give weak dynamics training signals, since the dynamics does not participate in inference. In contrast, some methods take a Kalman-based approach for learning inference models. This gives a better signal, but the models are often over-reliant on observations to correct prediction error, or rely on ground truth state for training. Finally, alternative overshooting methods also predict without taking intermittent observations, establishing an exclusive signal for the dynamics. In replay overshooting, we are interested in learning a dynamics model F and an observation model G through the Kalman filtering framework. In this work, we will use Z to denote the state of the system, which we call the latent state, and Y to denote the observation. Let's keep these dynamics and observation models in mind. Now consider these observations in the form of image frames generated from the dynamics of a controlled pendulum. These observations Y are subscripted with the time at which it was observed. Let's first assume we already have accurate models F and G. Now consider the inference time task of predicting image frames. In this example, we are given 5 frames and wish to predict the next 5 frames. The frames Y hat indicate that they are predictions from the model. The following procedure will be familiar to those who already have experience with the Kalman filter or recurrent time series models. We start with no input information and initialize the state distribution Z of 1 given 0. The measurement update is then applied, giving the distribution Z of 1 given 1. Note the dotted purple line, indicating the usage of the observation model. This is dotted since the observation model is not directly used to produce an observation. Rather, we use the measurement update equation to update the distribution of the latent state. The dynamics update is then applied to advance the latent state one step forward in time, producing Z of 2 given 1. Note the orange arrow denoting the use of the dynamics model. For simplicity, there is some loose usage of notation in the diagram, where the variables in the diagram are denoting the mean and covariance from the Kalman filter algorithm. We can now repeat this process of applying the measurement and dynamics update to produce Z of 5 given 5. This is the best estimate of the distribution of the latent state at time step 5, given all 5 observations. Note that this filtering step can be done without the need of a separate inference model. This process of computing the latent state Z from Y is known as posterior inference. It is common to denote the posterior distribution with the letter Q, and we follow that convention here. To complete the prediction task, we first need the latent state at future time steps. This can be done by rolling forward the dynamics model, giving us Z of 6 given 5. We can now directly apply the observation model to produce a distribution Y hat at time step 6. This procedure is repeated to produce the rest of the predicted frames. So how can we produce such a model that has accurate long-term predictions? Let's walk through the replay overshooting algorithm. Again, we are given our dataset of observations y. We would like to train our model to maximize the likelihood of these observations. First, the dynamics and observation models are initialized. We take a batch of observations y and compute the filtering posteriors, just like before. The smoothing posterior can then be recovered by applying the RTS smoothing algorithm. From here, we can use the observation model to produce predictions y hat. Given these distributions, we can compute the variational lower bound on our original objective. More details on this lower bound for time series models can be found in the paper Learning Latent Dynamics for Planning from Pixels. And while this does work reasonably well, we would like to further encourage the accuracy of the dynamics model for long-term prediction. The extended Kalman smoother already gives us z of 1 given 5. From here, we can roll forward the dynamics and predict the future latent states and observations. These replayed latent and observations are denoted as z bar and y bar. RO adds an additional loss term that encourages the likelihood of these observations to be maximized by these replayed distributions. The idea is that this will allow for more accurate long-term prediction. We put these two losses together and arrive at the variational RO objective. From here, we can optimize this model and run stochastic gradient ascent and maximize this objective. The variational lower bound on the likelihood objective is well explored in prior work. We apply this lower bound since we only have an approximate posterior distribution and can't represent the desired likelihood objective. However, this density is well studied in time series analysis. We can factorize this density using Bayes' rule, and in the linear Gaussian regime, the Kalman filter equations allow us to exactly represent the probability distribution of the observations using the filtered distributions. And since in the EKF we apply the linear Gaussian simplification to our nonlinear dynamics, we can take it one step further and also use the linear Gaussian factorization as an approximation of our original objective. This gives what we call the surrogate objective. When using this approximation, we likewise modify the RO portion of the objective and use the replayed distributions instead. To summarize, in the variational objective, we take a lower bound of the true objective and use the Kalman smoothed posteriors. In the surrogate objective, we use the filtered distributions and take a linear approximation of the objective. We examine the qualitative differences from using each objective on data from a van der Pol system. The variational objective suffers from high variance due to the use of the reparameterization trick and overfits to the observations. On the right, we see the model trained with the surrogate objective, which is less prone to noise and has more accurate dynamics. This is consistent with other experiments where the surrogate objective empirically performs better on most metrics. Next, we compare various overshooting methods. We place overshooting into three categories: branched overshooting, in which the dynamics are rolled forward for prediction on each time step; sequential overshooting, in which the dynamics are rolled forward after filtering; and replay overshooting, where the dynamics are rolled forward from the initial starting state. We compare the accuracy and uncertainty of branched overshooting used in the planet model and replay overshooting used in our model. In this clip from the test set, the pixel values of the pendulum mass in the red box are denoted in orange. Now consider the branched overshooting method from planet. We can output a belief over the pixel values denoted by the histograms in purple. Not only are the means frequently incorrect, but the beliefs are also very peaked, indicating overconfidence. In contrast with replay overshooting, the means are often more accurate, and when they are not, the distributions are wider, indicating that the model is more uncertainty aware. We further explore the use of RO by ablating on the pendulum system and evaluating prediction quality. Shown are two latent manifolds from the Kalman smoothers, the left with RO and the right without. The RO manifold's shape suggests that the latent space encodes angular information. The other manifold is unstructured and the trajectories are much noisier. We can also examine the prediction quality in observation space. Here is the ground truth of the oscillating pendulum, with the pendulum boxed in red. These are the predictions from the models with and without RO. If we examine the error between the ground truth, we can see that without RO, the predictions deviate severely. We also evaluated on the MIT PUSH dataset. This is a real-world robotics dataset collected and introduced by Yu and collaborators in the paper More Than a Million Ways to Be Pushed, a high-fidelity experimental dataset of planar pushing. It consists of many trajectories of a robot pushing an object across various surfaces. Again, we contrast the predictions of various models. The data are in gold and model outputs in purple. We see that both the surrogate trained models with and without RO outperform the planet model with more accurate mean predictions and more robust uncertainty quantification, especially where there are sharp changes in the trajectory. In contrast with the image prediction task, we find that the performance of the surrogate trained models with or without RO are similar in low-dimensional observation spaces. We hope to study these effects as well as integrating RO with control synthesis in future work. Thank you for your time. If you are interested in exploring replay overshooting, we invite you to visit our GitHub repo, where we have made the code publicly available.